Hi everyone, my name is Pranay Manocha and today I'll be presenting our paper SQAPP No Reference Speech Quality Assessment via Pairwise Preference on behalf of folks at Princeton and Adobe Research. So let's get started. Accurate and reliable assessment of speech quality is critical for a wide range of real-world applications like telephony, voice over internet protocol, and hearing aids. Sound quality is typically an assessment of the accuracy and fidelity of audio signals. In modern applications, it also encompasses listening experiences as well as aesthetic quality, which is also why the gold standard for SQA is the evaluation by humans. However, these subjective evaluations are not scalable and can be time consuming and costly as they often need to be repeated multiple times for each recording. Therefore, automated objective quality metrics are much more practical. Objective metrics can be grouped into two categories: full reference metrics and no reference metrics. Full reference metrics typically correlate well with human perception and may also be differentiable, but the requirement of a paired clean reference limits its applicability to real-world scenarios where the paired clean reference may not be always available. Moreover, since these similarity metrics estimate the distortion with respect to a reference, they can sometimes fail to reflect absolute quality. So in the given figure, we have subjective audio quality on the y-axis and different acoustic setups on the x-axis. We first select a random recording audio A on the plot and then select reference recording reference 1 that has similar acoustic setup to audio A. The length of the arrow denotes the similarity, and we note that audio A and reference 1 are very similar and therefore have high quality. We then choose a second reference, reference 2, that is equally high quality as reference 1, but has a different acoustic environment and is therefore less similar and hence lower quality than audio A, even though both reference 1 and reference 2 have equal qualities. On the other hand, no reference metrics are trained to estimate the quality without any given reference. Metrics like DNS-MOS and NISCA are trained directly on a large dataset of human ratings like mean opinion scores, MOS, and correlate well with human perception in a constrained setting, but fail to generalize across unseen perturbations. Moreover, collecting such a dataset is an uphill task and requires considerable resources like uniformity with respect to hardware and listening environments amongst raters to ensure consistent ratings, and even then have extremely high variance that may pose challenges in training robust models. Finally, ratings from multiple MOS tests cannot be compared and combined since the ratings depend on the stimuli considered. In this slide, let's compare the absolute rating model with a pairwise preference model. Given any quality assessment task, for example, say given a bottle of wine and asking you to rate the quality on a scale from 1 to 5, humans may have a large variance in answering this, even considering the same individual, by doing multiple judgments for the same stimuli. In the next scenario, we give a pair of examples, that is 2 wine bottles, and ask which out of the two is of better quality. Humans typically find preference judgments easier than assigning ratings on an absolute scale, and therefore these tend to be more robust and much more repeatable with much lower variance. The key idea that we are trying to explore in this is to obtain a low variance estimator for speech quality by training a model using pairwise preference, and 2, all these pairs can be produced entirely using simulation. Therefore, our focus is on creating a framework that is usable in real-world settings that does not require any reference. Moreover, the dataset should be easy to curate and should have low variance, making it easier to train neural network model upon. So based on these features, we propose our framework SQAPP that stands for Speech Quality Assessment via Pairwise Preference and therefore has a lower variance. The other benefit of pairwise preference, as we already mentioned, is that we can completely rely on synthetically produced datasets, for example, a recording with different levels of noise added, where we assume that more noise means lower quality. Our SQAPP framework takes in 2 speech recordings as inputs, audio A and audio B, with their magnitude and phase spectrum respectively. It is based on the pairwise preference objective, where the dataset is composed of pairs of recordings with each with the preference labels of which audio has better quality. In stage 1, we train a preference predictor to make the model learn content invariance, and in stage 2, we detach the preference predictor and use a new rating predictor that outputs a rating for each recording, following the same objective of optimizing on pairwise preference. Note that these pairs can be created entirely using simulation. Let's take a look at it in some more detail. Now let's take a look at how we create this dataset in the first place. We first assume access to a large clean dataset of clean recordings from which we select 2 clean recordings. Next, we also assume access to a big dataset of noise recordings, and these noise can come from different categories and can be of different types, including noise, additive noise, equalization, reverb, compression, frequency masking, clipping, and many more. And then we select any 2 levels of noise and add it to the clean recordings to create and synthesize these final recordings, which we call audio A and audio B. Also note that while creating these recordings, we have these noise levels, and so we have the actual label of which audio is of higher quality. And in this case, audio B, since it has a higher SNR, is of higher quality. Let's now take a look at the training procedure in action. So given these 2 recordings that we had previously, audio A and audio B, we first pass them through an embedding block, which is based out of an inception architecture, which uses small filter sizes and learns a good feature representation. In the next step, these embeddings are passed through a temporal aggregation step using temporal convolutional networks, TCNs, where its job is to learn an aggregated embedding for each time frame. And finally, in stage 1, we have a preference predictor, which is a 3 convolution layer model, and its job is to predict a probability score of which input is of higher quality. And this stage is trained using a smooth binary cross entropy loss. In stage 2, we detach the preference predictor and attach a new model, which we call the rating predictor, whose job is to output a single rating for each audio recording. And this is also based out of 4 convolution layers, and this is also trained using a softmax scale cross entropy loss. Now coming on to evaluation baselines, we comprehensively evaluate our metric SQAPP with existing full reference metrics like PESC and CDPAM, along with existing no reference baselines including DNS-MOS and NISCA that were trained directly on a large dataset of MOS ratings. And finally, we also compare our approach with a non-matching reference-based approach called NARESCA that was trained to predict relative SNR and relative SISDR between 2 recordings. Also note here that NISCA is trained on a model for full bandwidth, which is 48 kilohertz, whereas our model works on 16 kilohertz. Now let's take a look at the evaluation datasets. We consider 16 different datasets spanning across different categories of audio and speech tasks, including speech synthesis tasks, including VOCO and F15net. We also consider various types of speech enhancement tasks, including dereverberation and hi-fi GAN, and also the very well-known noisiest dataset. We also consider voice conversion as one task, including datasets from voice conversion challenges in 2016 and 2018. We also consider source separation, audio source separation, and sound source separation as two different types of datasets, and we have a large category of specific datasets that handle that. Now coming on to more specific degradations, we also have a dataset for telephony degradations, and then we also have a dataset for bandwidth expansion, which consists of very subtle differences. And lastly, we also have this general dataset, which consists of some common degradations, including additive noises and reverberation. And in terms of metrics, for each of these datasets, we try to correlate their MOS ratings with the output from our model using Spearman's rank order correlation for the MOS scores. And in datasets where we have the triplet scores, we try to calculate percentage accuracy of how accurate our metric is with respect to human evaluations. Here we show the MOS correlations and the triplet accuracies on the evaluation datasets. For more details, please refer to the paper, but here I'll only briefly discuss a few interesting observations. First, we observe that SQAPP is comparative to full reference methods, including PESC and CDPAM, as well as no reference models, including DNS-MOS, NISCA, and NORESCA in all cases, even without requiring any access to label data, which suggests its usefulness in these MOS prediction tasks. Next, we observe that our model SQAPP performs equally well for datasets having large differences, for example, dereverberation, as well as for datasets that have extremely subtle differences, for example, phase differences in F15.net. We also observe that our model has this advantage of being adaptable to unseen test degradations, for example, for audio source separation and for voice conversion challenge. And specifically, we observe that DNS-MOS and NISCA do not do extremely well in these two scenarios. More generally, we observe that NISCA performs better than DNS-MOS, and the hypothesis there is that since NISCA is trained on a dataset that has more number of judgments for every recording, therefore it has a much smaller variance in the dataset. And this is precisely the hypothesis why we are building a low variance predictor in the first place. We also observe that SQAPP performs better than NARESCA, especially across cross-perturbation comparisons. And finally, looking at the triplet scores, we observe that SQAPP outperforms DNS-MOS and NARESCA in all cases and is extremely competitive with NISCA, even though NISCA works at 48 kHz. Let's now talk about some of the other discussion points. To show the usefulness of our pairwise preference objective, we train a model directly on PESC, and this approach suffers from mode collapse and variance in the output distribution, wherein the model outputs the mean of the PESC score for a test recording that has more than one possible references. In the second scenario, we train another model without stage 1, that is without enforcing content invariance, and see that the model generalizes poorly to unseen speakers and content. This further suggests the usefulness of our pairwise preference strategy and our two-stage approach. Now one may wonder, why do we train with the two different speech recordings? So in the second scenario, we train a model with parallel reference and see that this model performs worse than the non-parallel content scenario, which shows the usefulness of content invariance in MOS prediction tasks. In the second scenario, we train another model without phase input representation, and we see that the model outperforms and the model performs worse on datasets like F15.net that rely on phase differences. And all of these findings suggest the usefulness of our design choices while building up this SQAPP model. In the previous slides, we talked about how well a metric correlates well with MOS ratings, but here we'll talk about the differentiability aspect of SQAPP and show that adding it as a loss function in the demux speech enhancement denoiser improves subjective and objective scores as compared to our previous CDPAM work and the baseline demux ratings. It achieves this in a much shorter training time than the existing baselines, which shows the usefulness of SQAPP as an optimization criterion. Finally, in summary, we presented SQAPP, which is a model that does speech quality assessment via pairwise preference. We showed that it is competitive with existing baselines without even any subjective ratings which are required for training. And finally, we showed the differentiability aspect of our model by showing it as an extremely important optimization tool for training a speech enhancement model. For future work, our plan is to extend the SQAPP framework to be able to predict MOS ratings directly, as well as other attributes including pitch. Secondly, we would like to investigate whether audio similarity and in general full reference metrics are a good proxy for audio quality. So with this, I'd like to conclude my presentation. Thank you all for listening.